Hello everyone, this is Xianjun from openwifi project. Openwifi is an open source Wi-Fi chip design that was announced in fosdem 2020. This year we are here again. Nice to see you all. Although I cannot see you actually. Anyway, let's get started. We are a small software-defined radio group in the wireless group of ID Lab, IMEC Ghent University, Belgium. This is the agenda of my presentation. First, the openwifi project progress in the first year after online will be introduced. Then, with some further explanations and highlights. Next, I will talk about our community growth situation. Then is the idea of low-cost hardware, which I believe will boost our community a lot. The last one is the roadmap of 2021. Come on, some of you might think this presentation is not as interesting as last year, right? No worry, let me show you something cool. I remind you, this is not a joke. Okay, that's all for today. Thank you. Any questions? I'm joking. Let's get started the boring part. And you can prepare questions meanwhile. The first thing is about how do we decide the release name, Ghent, Taiyuan, and Leuven. Actually, before the project online at the end of 2019, we, 3 developers, agreed that for each release, a developer will pick a name of a place on the Earth to assign it as the code name. Wait, on the Earth or in the universe? I can't remember clearly. Maybe it should be in the universe. After all, Elon Musk is going to live on the Mars. But the first 3 releases will be named by me, Wei, and Michael, which is the order of joining the project. I create the project at first, then Wei helped me a lot on open OFDM project porting and testing and many other stuffs. Michael wrote the OFDM transmitter and also did lots of work to enable the 11N feature. So the first release name, Ghent, is chosen by me. Ghent is the beautiful city in Belgium where we work. The openwifi was born in Technology Park, Ghent, where our office is located. The second release name, Taiyuan, is chosen by Wei. Taiyuan is her hometown and also the capital of Shanxi province of China. The third release name, Leuven, is chosen by Michael because he lives in Leuven, which is another beautiful city in Belgium and close to Brussels. The future release will be decided by the developer who contributes the most to the release. This will show respect to the people who actually did the job. Talk is cheap, show me the code. Next highlight, CSI. CSI means channel state information. For physical layer researcher, it's also called frequency response or channel transformation function. Anyhow, the CSI, I believe, is available in all the Wi-Fi chips, but few of them expose the CSI to you. As openwifi is designed by us, so we can expose CSI definitely to external environment. For instance, now you can access CSI very easily on openwifi via our set channel. Actually, we can expose more than CSI. So here I can call CSI chip state information. A typical usage of the CSI is to detect the object in the environment. For instance, human movement, human gesture, people falling down. For instance, in this picture, and the link is here, this is a paper, you can find lots of paper about CSI application. They collect the CSI from the transmitter to the receiver. The transmitter could be the AP in your home, right? And they collect CSI at receiver and running machine learning or classification algorithm to estimate or detect what is in between the transmitter and the receiver. Here, the human gesture is an example. I think it's a very interesting application, and lots of companies are working on this to count people, detect people. But apparently, there will be some privacy concern. As you can imagine, if I am a bad guy, I can receive your AP signal from outside your house and try to detect something inside, right? So CSI is just a tool. Use it in a good way, bad way, depends on people. So how can we protect people from the bad usage of the CSI? Here you can find a work from one of our experimenter in the Orca project. It's called CSI Murder. Murder the CSI. Here is the link. You can check all the details online. Basic principle is also not difficult. Since the openwifi chip is designed by us, we can add some random or fake CSI before the signal leaves the antenna of the transmitter. Then in this way, when you try to collect CSI via the receiver, actually you collect the combined CSI of the actual CSI and the fake CSI. So with this fake unknown CSI, your machine learning or classification won't work anymore. So if a Wi-Fi AP or some transmitter could give people this option, then people will have right to let the CSI work or not. I think that would be a good progress of the CSI technology. Actually, follow this direction, you can imagine lots of interesting papers or research, right? Because it's attack, defense, there will be endless work, I think. Next highlight is about the IQ sample. I guess all the people in this room know what is IQ sample because most of the SDR device offer you IQ sample streaming from antenna to your computer or from your computer to the antenna. With openwifi design, definitely we can also do that, but here we present you IQ sample in a different or in a clever way because our IQ sample capture function is under a trigger condition. We won't do streaming to the computer. Our IQ sample capture is triggered by the signal inside IPGA, by the event. For instance, the event of decoding success, the event of preamble detection, the event of the channel from idle to busy, the event of the channel from busy to idle. We have defined 32 events for you to select when you capture the IQ sample. So why do we develop this feature? The original purpose is for ourselves to debug our design, because at the beginning phase, we realize our low-level MAC is not ideal. We generate a lot of collision in the air. So the question is, how can we capture the collision moment and then debug further of our IPJ design. Then we find out this idea, IQ capture. For instance, how do we use the IQ capture to capture the collision? We do it like this. We set up normal communication between open Wi-Fi and peer Wi-Fi station via the main antenna, right? But on our platform, there is a secondary antenna. We call it a monitoring antenna. We can put this antenna via cable close to the peer Wi-Fi station. Then we set the IQ capture event be that we are transmitting. Meanwhile, we detect the RSSI from the monitoring antenna above a threshold. Actually, this means when we are transmitting, the other side is also trying to transmit. That means a collision in the air because the packet will be overlapping in the air. So in this way, we capture the collision, we analyze what happens in our IPGA, analyze the time before, time after, you can define the capture position, how many pre-IQ sample could be stored. It's a powerful tool. And the secondary usage could be that help you debug your receiver. For instance, if you set the trigger condition to the CRC fail, then you can capture all the Wi-Fi packet that is not decoded successfully by our IPGA. Then we do analyze offline on those IQ sample in MATLAB, in Python, to optimize or improve our receiver algorithm. And the third usage, apparently there are two antennas. You can already capture dual antenna IQ samples and to develop or verify your MIMO algorithm in the early phase, prepare for the MIMO development. Okay, the next highlight is application nodes. Actually, we learned this from those IC company and SRS LTE, because we noticed that SRS LTE also prepare lots of application nodes document online. We have set up the application nodes document directory in the GitHub. Currently, there are 9 application nodes covered from basic usage in different modes until the Wi-Fi 4 introduction and the packet injection. It's very useful for test. And apparently also the CSI IQ capture stuff. Definitely, if you want to explore those potential areas, potential usage of our platform, do check out the application notes. These highlights cover lots of things, essential updates, as you can see in the video. I cannot go through them all in this meeting. What I want to say is that they are really, really important. For instance, at the beginning, user keep telling us sometimes they encounter the kernel crash, kernel panic, or the driver crash. And we spent lots of effort on this. Finally, it pushed us to do a better design for the FPGA ARM interaction mechanism. Because for processor system, you can never assume the processor will handle the interrupt in time. The interrupt sometimes is handled in time by the processor, but sometimes several interrupts, they are queued and they are delayed, and they arrive the CPU or wake up CPU suddenly in a very short time. So lots of state information have to be stored somewhere. You cannot drop them because you don't know when the processor will process them. Anyhow, lots of details between the Wi-Fi driver and IPGA hardware. You can feel the big improvement if you run our current design versus the initial design. Okay, next topic is about the community engagement or the community growth situation. I would say we did a good job regarding this. If you check the openwifi GitHub in the 1 year period, we got 1.6K stars. That's already a lot, I would say, in this very narrow or professional domain. And 200 folks, around 100 watch, and several issues still open. 3 internal developers you have known before, and with also 3 external contributors, surprisingly. Although their code hasn't been merged yet, but I believe some of those code will be merged in this year. But if you compare our project to another very hot IPGA project in the processor domain, the Rocket chip, the leading chip design project of the RISC-V domain on GitHub. They are online for 2 years, and some company, I think, already tape out the Rocket chip. They have 1.7K stars, more or less the same, but they have much more forks, watch issues, and contributors. Apparently, their community is much bigger and more active than ours. I think the reason could be related to the question I raised to you last year, why the computer science domain is so open and the connectivity domain is so close. I don't know why. But there could be also some other reasons. For instance, people maybe are so satisfied with the commercial Wi-Fi chip to play with, no matter for hacking, for security research, or for IoT application. They are quite happy why they will use open Wi-Fi. And maybe because we are lacking the killer application of features that can only be done via open Wi-Fi. Actually, we are offering some of them, like the CSI murder IQ sample. I think more will come. For this part, we are also eagerly want to hear from you. The third reason could be that the Linux driver stuff, as I mentioned before, the processor IPG interaction and IPG development are too difficult for many developers, because I think maybe the user space program is a bit easier for most of the developers, because your software run in a pure CPU environment, no external interaction. And the last reason could be that the hardware is too expensive. Although we have tried hard to push our design to a cheaper platform. For instance, at the beginning, our design ran on a SASE 706, which costs you around $4,000. Now we can run on Z-board plus RF, costs you only $900. It's already a big push, but a Wi-Fi chip only costs you $50, even less. There's still a huge difference. I think this huge difference sometimes make the people difficult to make decision. So if you have any idea or theory about the reason, do come and tell us. We really want to grow the community. Okay, regarding the low-cost hardware, I have been looking at the possibility for a long time. The final conclusion is like this, not final conclusion, initial conclusion. I believe the open Wi-Fi, the cheap open Wi-Fi platform could be, the price could be as low as $200. Some of you already seen a several days discussion on Twitter about the chip and hardware price at the end of 2020. I guess during that time, lots of people had holidays, so we have time to do the discussion. Anyway, I also discussed in person with many hardware makers in Western and in China. I feel that in the future, there will be a cheaper open Wi-Fi platform. The price would be around $200, even cheaper. Let's see. New feature planned. Well, we have spent 1 year to realize there isn't any feature that is easy. Even a small feature, a bug fix, all things are not easy actually. So we will be very careful to plan new features regarding the difficulty and the resource we have. So in this year, we will start to work on the Wi-Fi 6 or 11AX standard. This year, maybe the basic physical layer, transmitter, receiver will be developed. And also the MIMO. since we have prepared some basic tools like the dual antenna IQ capture, and we also have some master thesis working on that. So MIMO will also be started. Start from the antenna switch or diversity receiver. Let's see what can we achieve in this year. Maybe during summer, we could also make a proposal to Google to hire some students via the Google Summer of Code. I don't know. Let's see. Breaking news. I think this is the big news this year. Always big news comes at the end of each year, right? Last year, openwifi, this year. The Blade RF. Blade RF, they also released the Wi-Fi design for their FPGA on their SBR board. Although their design and our design, there are lots of difference. I think basically we do the same domain, design the Wi-Fi hardware, the chip via the FPGA. I think this is a good sign also for us. That means in this community, the Wi-Fi FPGA design is an actual need from the community, not only our imagination. So we will keep watching and well, let's see. We hope this could encourage more and more people to think about playing the Wi-Fi in a very deep level, deep into driver and FPGA, to come up with much more wild ideas. A quick recap of today's presentation. First one is that we have made lots of progress on different aspects in the first year online. I'm proud of the project and our developers. We will push further for the advanced features like the Wi-Fi 6 and MIMO, but we realized they cannot be done in one night, but we will keep moving. And for the community, we will also try harder to grow it. Regarding this point, we do need your help. Your help is very welcome. Even you never use our design, but you can mention it, right, to some other people you think our design might help them. That's also a very good help. And thank you in advance. And finally, the breaking news, another Wi-Fi FPGA design. I think that means more people will join this deep layer, deep Wi-Fi playing domain. We will keep moving, keep watching. Sometimes competition is good for the ecosystem. All right, this time, this is the real end of my presentation. Any questions, please do communicate with us. Bye-bye. Hi. So, okay, most voted question from Daniel about the CSI functionality. Yeah, yeah, this is quite good question. So the basic concept is that we involve a fake channel response at the transmitter. So if we consider a very simple single antenna communication scenario, if the real channel is AWGN, right? If we add the fake frequency selective channel on the signal, then I guess the whole link will be degraded. After all, it turns from AWGN to a frequency selective channel. But the real case is like this. If you monitor CSI for a normal Wi-Fi link, there's always frequency selectivity, either caused by the RF or caused by the multipath. So in this case, when we add some slight frequency selectivity at the transmitter, I don't think it will bring a big degradation to the whole system. So the basic principle is that we make sure our fake CSI is added after all the processing, just maybe before the IFFT, we add the frequency selectivity on each subcarrier, or after IFFT in the time domain add a filter. Then the receiver side doesn't need to know this. Receiver, or the whole bunch of receiver algorithm will treat the fake channel plus real channel as a whole, right? So receiver don't need to aware that. Receiver don't need to modify it. Work with the fake CSI. So yeah, but I believe for the MIMO case, could be more complicated. But the basic principle we should follow is that we add the fake channel after all the pre-coding beamforming operation, then let the whole inner part of the whole system as a whole, right? The fake channel plus real channel as a whole. If we follow this principle, the receiver don't need to be changed. There's one situation if the transmitter needs receiver to do the feedback of the channel state information to help transmitter to come up with the optimal precoding. In that case, I think the transmitter need to consider this fake channel added at the transmitter side, because the feedback from receiver will include the fake channel response. Yeah, but then the signal transmitted will also include that. I think lots of things could be down there in this anti-sensing or fake channel stuff.
So a second question came up just right now from Jan. Don't devices like BlueSDR, HackRF, RedPitaya, and others have an FPGA that could be suitable for Open Wi-Fi? And what is holding you back from porting to those platforms?
The basic reason is that FPGA on those platforms is too small for our current design. Our current design is a basic single antenna 20 macros, 11N design, 11 AGN. The smallest FPGA currently we are working on is 7020. On Bluetooth is 7010 FPGA. HackRF even much smaller. So we need bigger FPGA. Yeah, that's the reason.
Okay. Perfect. And then the probably last question that we can ask is, what is the main motivation to work on Open Wi-Fi? Like even after these the awesome work you did the last year, what is the main motivation for Open Wi-Fi to exist?
I think main motivation. Well, the first motivation is that we realized before our project, when people want to work on the chip level of the Wi-Fi design, if they want to test their new ideas on the chip level, they don't have so much freedom of free choices. They need the National Instruments Wi-Fi application framework, or they need the WARP design or the reference design for Mongo communication with restricted license condition with some license fee. So we decide to come up with free software design on this to help people have more choice, more free choices. And in this action, we also, I think, lower the whole bunch of the whole reference design software plus hardware. We lower the price a lot. So this could encourage more lab or university or group could jump into this field if they have a limited